Bhandari from ISI Bangalore, who's going to talk on the topic on ovenness of K-fusion frames. So, Animesh, please continue.
Yeah, uh, very good afternoon. First of all, many thanks to the organizers for giving me the opportunity to present my talk, present my work here. My research area is film theory. Now the question is why people will study films. Originally, film theory was introduced on separable Hilbert space, and if there is a separable Hilbert space, then it guarantees the existence of orthonormal basis. And using orthonormal basis, the Hilbert space elements F can be explicitly represented by means of respective Fourier coefficients, like F is equal to summation inner product F EI, where EIs are orthonormal basis. Now, in practical circumstances, when uh, that Hilbert space elements F are characterized as signals, and when a signal is transmitted through a noisy channel, if due to some technical reason, any one of the frame coefficient, that is Fourier coefficient in our product is removed, then at the receiver end, the receiver cannot reconstruct the original signal. Due to this fact, an overcomplete system was required. Such an overcomplete system is called frame. This overcomplete system is more flexible because of basis elements. The basis elements are linearly independent, but frame elements need not be. Title of my presentation is on openness of K-fusion frames. There are several generalizations of frames, like fusion frame, K-frame, and we have worked on intertwinedness of K-frame and fusion frame. We named it as K-fusion frames. My total presentation is divided into 5 sections. After discussing preliminaries and background results related to frame theory, then we will discuss K-fusion frames, properties of weaving K-fusion frames, and then we will discuss some of the applications. And to work work on K-fusion frames, we have gone through so many research articles, papers, books. Here we are acknowledging some of them in the reference section. This is the brief history of frame theory. The concept of frame theory came in the year 1946 by Gabor by introducing reconstruction formula. After a couple of years, in the year 1952, Griffin and Shepard, they first introduced Hilbert space frame, and after several decades, in the year 1986, Davichis and Grossman and Mayer, they first realized the importance of frames in different applications like signal processing, image processing, data processing, and many more. This is the mathematical definition of frame. Suppose we have a sequence xi in a separable Hilbert space H, then it is said to be a frame for H if there are two positive constants A, B, such that every Hilbert space element X, the given sequence satisfying this inequality, then the sequence is said to be frame for H. Here A and B are called frame bounds, where A is called lower frame bound, B is called upper frame bound. Frame bounds are not unique, so supremum of all such lower frame bound is called optimal lower frame bound, and infimum of all such upper frame bound is called optimal upper frame bound. Now, depending upon the nature of frame bounds, we will get specific types of frames. For example, when A is equal to B, that is lower frame bound is equal to upper frame bound, the given frame is called tight frame. In addition, when A is equal to B equal to 1, then the sequence, the given frame, satisfying the Parseval identity, and that's why the given frame is called Parseval frame. And whenever removal of a single frame element seizes the frame condition, this frame conditions, then the given frame is called exact frame. And whenever a sequence satisfying this right-hand inequality, then it is called the Bessel sequence. And in frame theory literature, there are so many generalizations. One such generalization is K-frame. This is the mathematical definition of K-frame. Suppose we have a bounded linear operator K. Then, if a given sequence Xi satisfying this inequality, then it is called the K-frame for H. Now, if we replace K by the idempotent operator, then the given frame becomes our classical frame. These are the examples of sequences which are framed, which are not framed. If En is orthonormal basis in L2 N, then the first example shows that it is a frame for L2 with frame bounds 1 and 2, whereas second example is a Parseval frame for L2. Since it is a Parseval frame, so optimal frame bound is 1. That is optimal lower frame bound and upper frame bound is 1. Whereas the third example shows that it is not a frame for L2 because for this sequence, we will never get any upper bound. That is right hand inequality of frame condition. So it is not a frame for L2. And throughout this work, we have used several times Moore-Penrose pseudo-inverse. This lemma shows the properties of Moore-Penrose pseudo-inverse. What it says, suppose we have two separable Hilbert space H and K, and if we have a closed range operator T from H to K, then the Moore-Penrose pseudo-inverse is denoted by T dab from range of T to H is satisfying these three conditions, these three properties. Also, for a given frame, it is a natural question. It is a natural interest that what are the characteristics, what are the properties for a frame operator for a given frame. To define a frame operator, first we will define the preframe operator or synthesis operator. The preframe operator P from L2 to H is defined by this identity. And the adjoint of the preframe operator is called analysis operator, defined by this identity. And the composition of preframe operator and analysis operator gives us the frame operator. One important observation that the frame operator is always bounded, positive, and invertible. And using the invertibility property, we can reconstruct the Hilbert space elements by this expression where the collection S inverse Xi is called canonical dual. Here we must say that duality is a very important thing in frame theory. This is the mathematical definition of general dual frame. If we have a frame Xi and if there is a sequence Yi, then this Yi is said to be dual of Xi if for every X in H, every X satisfying this identity, then Yi is said to be dual of Xi. This is definition of K-fusion frame. If K is a bounded linear operator and if we have a collection of closed subspaces with a collection of positive weights Vi, then the weighted collection Wi is said to be K-fusion frame for H if there are constants, positive constants A, such that every Hilbert space elements F satisfying this inequality, then the given weighted collection is called K-fusion frame. Here, PWI is orthogonal projection on closed subspace Wi. And here, if we replace K by the identity operator, then the given K-fusion frame gives us the definition of fusion frame. So, K-fusion frame is also generalization of fusion frame. And this is the mathematical definition of weaving K-fusion frame. Here, one may ask a question, what are the importance of defining ovenness of frames? Now let us consider a scenario. Suppose we have a collection of sensors, say X1, X2, Xn, and these sensors produce some result. Now, if some technical reason, any one of the sensors, say Xi, is removed, then the resultant may contain some error. So, to resolve this problem, if we consider another set of sensors, say Y1, Y2, Yn, who is having the same job as Xi is, then in place of Xi, Yi can replace and removal of Xi, Yi will serve the Xi's job. Such an intertwinedness between two sets of sensors or in general between two frames is called oven frame. This is mathematical definition of weaving K-fusion frame. Suppose we have a bounded linear operator K, and if we have two K-fusion frames Wi, Wi, Vi, Vi, then it is said to be a K-fusion, oven K-fusion frame or weaving K-fusion frame if for every sigma index set subset of I such that these two weighted collection satisfying this inequality. That is, for every sigma corresponding weaving satisfying the K-fusion frame condition. Then these two given K-fusion frame is called weaving K-fusion frames. These two theorems shows the properties, some properties of weaving K-fusion frames in different spaces. Here, we wanted to study the properties of one K-fusion frame to another K-fusion frame by defining a new bounded linear operator. First theorem says that if we have a bounded linear operator K in H, and if we have two K-fusion frames Wi, Wi, Vi, Vi in H1, and if we have operator, closed range operator T from H1 to H2, then this weighted collection, image of this two weighted collection under this closed range operator T forms a K-fusion frame. Here K is special operator Tk T star under these two conditions. And this theorem shows that this theorem is basically converse of this theorem. What it says, suppose we have two weighted collections, and if we have a 1-1 closed range operator T, and if we assume that for a given bounded linear operator K in L2, H2, LH2, such that the image of these two weighted collection under this 1-1 closed range operator are weaving K-fusion frames for range of T, then these two frames, the original weighted collections are also weaving K-fusion frames. Here K is T dab KT with universal bounds. Here we will study the properties of weaving K-fusion frames. What it says, suppose if we have a bounded linear operator K and consider two weighted collection of closed surfaces, and if we assume that these two weighted collections are weaving K-fusion frames, then these are also fusion frames for H, and if range of K is closed, then these two weighted collections are weaving fusion frames whenever they form weaving K-fusion frames for range of K. So in second condition, from K-fusion frame, weaving K-fusion frame, we will get weaving fusion frame. Here we study the properties of weaving K-fusion frames in the context of perturbation theory and in presence of eraser. The first theorem says that if we have two bounded linear operators T and K in H, in addition, let us assume that K has closed range, and if we give the perturbation in between adjoint of T and adjoint of K by this expression, then the two weighted collections are weaving T fusion frame if they are weaving K fusion frame for range of T. And this theorem says that if we have two weaving K fusion frames with respect to a bounded linear operator K with the universal lower bound A, and if there is a operator, bounded linear operator T, satisfying these conditions, these two conditions, then if we have an index set J, then the new weighted collection, these new erased weighted collections are also K fusion frame. Here K is T star, and this eraser is erasing by J components. And if this collection satisfying this condition, this inequality, then these two erased weighted collections forms T star fusion frames. In frame theory literature, there are so many applications. Here we mention some of them for signal processing, image processing, data processing, sensor networks. These are very practical like applications. Also in theoretical case, we can extend our work in reproducing kernel Hilbert space, because in literature we have studied that people have done the properties of reproducing kernels by means of ridge basis. Also, we can study the properties of reproducing kernel by means of frames, because frames are more weaker condition than risk basis. Because if we have risk basis, then risk basis automatically imply is a frame, but frame need not be a risk basis. Why? Because there is a standard theorem, sequence is risk basis if and only it is an exact frame. So if we consider any non-exact frame, then definitely it is not a risk basis. So in theoretical case, we can study our work in reproducing kernel, also in case of wavelet analysis, and these are the references of our work. Thank you.
Thank you, Animesh. Let's see if we have any questions from the audience.
Yes.
Yes. Yes.
So your weaving frames are more like replacements of Schauder decompositions.
Yes, ma'am. Yes.
Your weaving frames are more like replacement of Schauder decompositions.
No, ma'am.
I mean,
Hello.
yeah, I mean, you have bases and there is orthonormal base. You have Schauder decomposition and your replacement for that is these weaving frames.
No.
What is it?
Actually, frame, no. If there is a order basis, in
Yes.
basis, yes, in basis elements are more restrictive cases are there, because basis elements are always linearly independent. But frame
Right. But your frames, when you take subspaces, WIs and weights, they are more like Schauder decompositions.
so basically these are where closed subspaces are spans of given frames.
Thank you.
Yes.
Thank you, ma'am. Let's see if we have any other questions. Okay, so if we do not have any more questions, let's thank the speaker again. Thank you, Animesh.
Yes.